Test 1, 2, 3. Okay, now it's working. This notebook can be downloaded on GitHub, and I will show the link again at the end of the talk. We will learn about these libraries or modules. It's Shapely, it's for manipulation of geometric objects. Then we will go to the vector data processing. You have to know, today we look at two types of data, geospatial data. One is vector and the other is raster data. There are also data, geospatial data sets available like point clouds. We are not looking into this today. So then we look at rasterio. It's a nice way to process raster data. And we will see a little bit pyproj for different geo-coordinate systems. And then the best of all is GeoPandas. I think everyone knows pandas. May I ask quickly, who of you already heard of GeoPandas? Okay, quite 3, 4, 5 people. Nice. And then we make maps using volume. So I will use some public domain datasets. That's the easiest way. So I just put it on the GitHub account too, so you can just use this data. And let me talk about the two biggest libraries available for geospatial data processing. One is CHEADLE. If you know professional GIS software, these modules or libraries are always used. CHEADLE and GeoS are written in C++, and there are some bindings available for Python, but they are horrible. The documentation is basically a C++ documentation. It's really much guessing. And recently there were some pythonic implementations made out of these libraries. One is rasterio, the other is Fiona, and a very nice library is Shapely that we will see in an instant. And GeoPanda is made out of them. So it's a very small overview. Let me tell you how to install that. I really recommend using Anaconda. That's the simplest way. It's currently working up to Python 3.7. When 3.8 will come out, don't try it. It usually takes 4 or 5 months for all libraries to be updated again. So just do the conda install, Shapely, Fiona, rasterio, GeoPandas. But for volume and IPyLiflet, you need the version on conda forge. It's not in the base repository. So let's look at Shapely. Shapely is a library or a module for the manipulation of planar geometric objects. So this sounds interesting. What is meant about that? There is a standard, an industry standard called Simple Feature Access. It's a standard created by the Open Geospatial Consortium, OGC, and it's also an ISO standard. So it defines how these geometries are made. So point, light, line, polygon, multipoint. I made a small graphic. These things. So how do you define a polygon with a hole, for example? And once you learned about that, it's quite simple to create such polygons. So let me make an example. I think it's a little bit smaller. Make it bigger. Can you? Okay. Can you read it? Oh, it's too big. Like this, I think. Okay. It's too small, but I think if you are in the front row, you can read it. So you import the Shapely geometry polygon. Of course, you can, I go back quickly, you can use point, line string, polygon, multi-line string, multi-point, multi-polygon. Multi-polygon just means more than one polygon. And in this example, I just made a polygon. I define some coordinates. It's made with make tuples of the coordinates. You see it's 2D. There is also a way to create 3D polygons, but we are not looking at that at the moment. And then you can do some operations with this polygon. For example, here, the area of the polygon or the length. So you can also display this. You just write this polygon 1, and in the Jupyter Notebook, you just see this polygon. You also see there is no coordinate system. It's just, I say this is more or less for debug reasons. You can just look at it. So if you make a second polygon here with different coordinates, actually it's a triangle, then you see the coordinates, they don't really match. So it's really just for debug purposes, this displaying. But now you can do some operations, like a union of the two polygons. And if we look at the result, you see these two polygons intersecting, or a union of it, creates a new polygon. And if you ever write such code in Python or whatever language, it's really tricky to do these operations with polygons, especially 3D polygons. But even with 2D polygons, that is not an easy operation. Okay, so I can do intersection instead of union. So let's go back quickly to show what this means. The two polygons, but the intersection part, then you get a triangle out of it. Or you can do a symmetric difference. And here you see the result. That's actually a nice result because you have a hole in this polygon. Yeah, it's a polygon with a hole. And yeah, okay, we have triangles and easy geometry at the moment, but think about if we do whole countries with that. We can do some processing, we can do many things. We see that later. So of course you can do some stuff again with the result, like calculating the area or the length of the polygon again. These features are available in this module. Okay, let me show about one standard of the simple access OGC standard. It's called Wellknown Text. And Wellknown Text is a representation in text of such polygons. So if we look at the previous polygon, it was a multi-polygon. You can look at it and you see the coordinates. And this text represents this polygon. So you can write this down and create out of that a new polygon again. That's what I make. You see, this is just a string, this result. And out of the string, I can create, with the load string of the Shapely WKT function, I can load this again. So we can really save it as text and load it. Now maybe you wonder why text, why not binary? There is also a second standard, the well-known binary, WKB. But in the geo domain, it's very important to store such thing in a physical way, so you can print this and scan it again, so it's really stored. If, for example, if you have a country border and you want to save the polygon exactly, you can just print it out. Okay, it would be a much bigger polygon than that. So the last thing we look at in Shapely, there are some interesting binary operations. So you can check if a shape contains the other shape or intersects, and this works for point and polygon, for example. You can check if a point is inside the polygon. You can check if two polygons intersect. You can check if one polygon is within the other polygon or one line is within the other polygon, and all these binary operations. So we see polygon 1 intersects polygon 2, returns true, or polygon 1 is within polygon 2 is false. We remember it was a little bit outside, or if it's equal, okay, polygon 1 is equal. Polygon 1, that's true. Such things you can do. But of course, it's much more complex. You could do that with lines, points, polygons, all together, these operations. And that's really a tricky thing. These operations are really difficult to implement. Okay. So let's look how to load vector data. And the most important thing about vector data is vector data is not just geometry. What we saw before is just plain geometry. But for every point, we want, for example, additional information. Think about cities. We have all cities in the world, and one such attribute or property would be the city name, maybe the population of the city, etc., etc. So we have the geometry and properties always for this data. So let's look at one open data set. It's from Natural Earth. It's an airport data set with many, many airports, not all, but many airports inside. And we can just open this. The format is a shapefile. It's a common format in Geo world. It's created originally by Esri, and today it's a very popular format. So we can open this and look at the first entry. We see the first entry is just random actually. The first entry in this dataset is a airport in India. So we can take the properties name. We get the name, Sandoval. We can check what geometry type is it. It's a point. So for every airport we have one point. We don't have the geometry of the whole airport here in this dataset. And we can look at the coordinates. And we see this is probably a geographic coordinate, 75, 30, longitude, latitude, or latitude, longitude. We don't really know that at the moment. And yeah, let me tell you two ways to read such vector data. The one is if you have unlimited RAM, you can just load all data in a list. I personally don't prefer this because vector data sets are usually very big, so we don't have space. Or the other is just iterate through all elements and then access the data. So let me search for the Minsk airport. So I use the with statement, so I don't have to call close again. That's the only reason. So I open this airport dataset, read it, and go through all airports in this dataset. And I check if the IATA code is MSQ. Then I just print the properties, name, coordinates, and the Wikipedia link. The Wikipedia link is part of this dataset. So for all, or for most airports, there is a Wikipedia article. So we see the result is here. So now we also know what's latitude, longitude probably, 28, 53. So we have longitude, latitude. Talking about the coordinate system, there is a function to tell us which coordinate reference system is being used. And in this case, we see it's a EPSG 4326 is the result. And EPSG, oh, I didn't write it here. EPSG stands for European Petroleum Survey Group. This association looking for gas, and they have lots of money. So they collect these reference systems. And here is a web page. You can check this and see the definition of that. I can probably go quickly there. Oh, doesn't matter. Now I screwed everything up. No problem. Just go full screen again. So you can check it when you download the presentation and have internet. Doesn't really matter at the moment. So let's look at another data set. I have a second data set here. It's admin 0 countries. It's a data set. It's also an open data set where we have the polygons of every country in the world. And admin 0 means it's really the country. In case of UK, we have UK as a country and not England, Scotland. That's meant with admin 0. And we can open this too and iterate through all. And we can look at the first entry in this dataset again, and we see this is Indonesia. It's just random, it's the first dataset. We can look. Oh yes, in this dataset we have different languages. So we can check the name in Chinese, and of course in Russian. I don't know if it's correct. My Cyrillic, Indonesia, yeah, it seems it's correct. And the continent of this country, Asia in this case. Yeah. And the last is not visible because I made it too big. We can check the population and the year when the population was determined. So that's a really big country. Okay. So let's find the Belarus polygon. I do it's actually the same code like before, more or less. I just check all properties name. I look if it's Belarus, then I print country, population, when this was done, 2017, and then I have the geometry. I store that in the name geometry. You see, geometry is the country. Geometry is a polygon, and we have is, I don't know if it's correct, 9.5 million. Is this correct? It's about 2017. So now let's do another thing. We want to see which airports from the first dataset are within the Belarus polygon. So we can take the Belarus. See, this should be correct. Belarus polygon, and we plot it here. And then in the next step, I just check. I go through all airports, and I say, okay, if this position of this airport is within, and we have this geometric operation within, this binary operation we heard about before, and we see this dataset only has one airport. I guess Belarus has more than one airport, but this dataset is not complete, so that's a pity. Probably I didn't check it, but I'm sure there are some military airports and other airports which do not contain. So it's open data, so everyone can add this to this. Okay, let's go to the next thing. We learned about vector data a little bit, and now I want to go to the raster data. So raster data is pretty easy. Everyone knows it, more or less. It's like a JPEG image, but the difference is we can have more than 3 channels. So it doesn't have to be RGB. We could have, for example, a near-infrared channel or a multispectral channels. But in this case, we will still look at the RBG dataset. I have a Blue Marble dataset from NASA covering the whole planet. And we can just open it, rasterio open, read, and we see the dataset has a name. It's just a file name. The dataset has a mode, and we are reading it. We don't write it or destroy it. So if there is an R for reading, it's all safe. And with count, we can check the number of channels. As I said before, we have RGB. It's red, green, blue. Probably if you have 3 channels. And we have the indices of this, so 1, 2, 3. It doesn't start with 0, so have to be careful. So red is 1, 2 is green, and 3 is blue. And we can also look at the width and height of this dataset. It's a rather small image. There are bigger versions available for download by NASA, but I didn't want to fill up the GitHub space. And now we can check again the coordinate reference system. And we see again, it's EPSG 4326. So it's a geographic coordinate system covering the whole planet. So also the bounding box, we see it starts minus 180 up to 180. So we cover really the whole planet. Okay. And the next thing is these datasets, they have more than just pixels. We need to know the coordinate transformation. So we can calculate some things. It's an affine transformation. So we can, for example, take a pixel coordinate, 0, 0, multiply this with this transformation, and we get the geographic coordinate out of it. We can also do the inverse transformation. So we take a pixel coordinate, we take a geographic coordinate, 0, 0, will be in the middle of the Earth. At the equator and Greenwich. So we have a pixel coordinate 1800, 900, and if you remember correctly, it's in the middle of the picture, so that's correct. So we can also check what pixel coordinate does Minsk have. Okay, Minsk is not a pixel, so I took here, exactly here, this coordinate, and multiply it, and we get the coordinate 2074, 361. You see, it's a double representation. It's not an integer, but we can make an integer out of it. It's no problem. We can round it 2075, 361, and again the bounds. and we want to display that. So we take NumPy and pyplot, and I read RGB, the 3 channels, and what I get back is R is a NumPy array with all red pixels, G is a NumPy array with all green pixels, and B contains all blue pixels in the NumPy array. So it looks like this. So nothing spectacular. What I did, by the way, is I did a stack with RGB, so I have red, green, blue just together. So 15, 27, 51 would be RGB for 1 pixel. And if we have this array of pixels, we can just plot it using matplotlib, ImageO, and I also plot the coordinate Minsk, IVV, but you see it's this small, so Minsk is really just a pixel on this dimension. Doesn't really matter what coordinate I took, but it seems to be correct, I hope. Yeah, it's correct position. So, and we see also here the axis are in pixels. We could change that to geographic coordinates, but I leave it to pixels. And we also see that 0, 0 is the top left position. Okay, so let's combine most of that and come to GeoPandas. Do I have time? Yeah, I still have a little bit of time. GeoPandas is basically pandas, but with geo. That's why the name is GeoPandas. It's really very simple. We can read a dataset with pandas, like here. This dataset contains all cities of the world with more than 5,000, with population more than 5,000. So I open it, it's UTF-8 encoded. It's a really big dataset, so I'll use low memory false, so extend the memory. And say there is no header, that's true, and I get really all these images. It's a little bit small here. Here's just a city name in original name, and here the city name in English transcript, and here it is all languages. So even Japanese here. We have all. It's a complete data set. Here's the population and so on. So let's look a little bit closer. I make it bigger for you. So I just take 4 columns. I don't want to look at the whole data set at the moment. So I just take the columns 1, 4, 5, and 14 and give it names, name, latitude, longitude, population. It's just because I don't want this really large data set, so I can display it here easier. So I can do query. It's pandas, not GeoPandas. Just get Minsk, coordinate, population. We see this population is different. Oh, before we had the whole country. So 1.7 million. And now we come to GeoPandas. GeoPandas is, as I said, pandas, but there is a special column. This column is called geometry. And in this geometry column, we have a WKT description, or better, we have a shapely object inside. So I can just convert my pandas data frame to a GeoPandas data frame. I zip this longitude, latitude, and name it geometry. So I use the geodata frame with this old data frame and add the geometry column. And we see now in the last column is this shapely object. So in this case we have points. Every city has a coordinate, latitude, longitude, and population. And what I do next is I drop the longitude, latitude, because we don't need it anymore. So yeah, then I plot it. Geodata frame has a method plot. So I can directly plot all cities of the world with bigger than 5,000, the population bigger than 5,000. I use a marker size 1, so it's 1 pixel. And I make it a little bigger so you can see it. And I think you recognize our planet, but it's just cities, just points with cities. So it looks pretty nice. So we could also export this dataset to a different format, for example, shapefile. I commented it out because I don't want to upload it to GitHub. It's really easy to export. There are different formats. You can also export with GeoJson and many different geo formats. So let's again look at this generated city dataset. I call it cities, so we have a better name. Look again at the dataset. It's the name, population, and the point. So remember the name cities. And so I can do queries like we know that from pandas. I want all cities that have a population bigger than 10 millions. So yeah, and I sort it. Just sort values, ascending false, and I get the biggest city in this dataset is Shanghai, followed by Istanbul, Buenos Aires, Mumbai. Yeah, you see, you can do the same stuff like you can do with pandas, but you can also plot everything. So let's look at something else than points. We look at the admin0 country dataset again. So I read it directly because shapefiles are supported by GeoPandas. So I can just read this shapefile with all countries and display the first 5. And what we don't see here on the other side would be the polygon. I can show that here in the last. You see polygon, and you see the coordinates of everything. What we also don't see here, some countries are multi-polygons. Think, for example, USA with Hawaii. So it's more than one polygon. You have to consider that. And so I just make a charter again. I make countries too. I'm just interested in name, population, and geometry. I make small again, so if it's too big, I can't really display it very good. So let's take the reduced dataset. Ooh, here's a small problem. And we can search again Belarus and save it as BY. And we have here the geodata frame of Belarus. We can plot it. And you see this is automatically done by matplotlib now in the background. So we have the correct coordinates. You also notice, I think you all know the country very well. You also notice there is a little bit stretched. So why is that? Why is that? It's because, yeah. Exactly, because of projection, we have geographic coordinates, and geographic coordinates are always not equal area, so the area is wrong here. We will see later the whole planet, so we can take, what I didn't show you is I take here the countries where the name is not Belarus, yeah, so, and plot it here. First I plot Belarus green, and the rest of the world is black, and plot both together. You can do that using the axis object. You can do that. You could do that with several countries. And here we see it's a geographic projection. It's a plot carré projection, or and it's just the coordinates mapped to a map, and so it's all not in an equal area. So we can access the geometry of the polygon using ilog geometry, and we can test the type. We see Belarus doesn't have islands outside, so it's just a polygon. And we can say, I take the cities, remember the cities dataset from before, with all cities bigger than 5,000, with a population bigger than 5,000, and we can combine that, cities within, and I take this geometry, so within this Belarus polygon, and here we see the first 10 cities with bigger population than 5,000. I use the English transcription text, not the original. So excuse me that. So we come to the next. And last, let me see. Ooh, I'm late, but I think I have 5 minutes. It's okay. The last module, it's called volume. And volume is nothing else than leaflet. Leaflet is a mapping API written in JavaScript. And volume is a Python module which generates automatically JavaScript plus HTML and displays maps in the Jupyter Notebook. So with 3 lines of code, I can create a map here and display something and open it and have a map on the screen. So we remember our polygon from before, BY, the Belarus polygon. And with a few lines of code, we can add it to the volume map. We just say I would like a GeoJson created from this shapely object, BY, and add it to the map. And we see now, we don't see it good, but now we see this one is the Mercator projection, and it's equal. It's really the correct shape now, more or less. But you know the problem of the Mercator projection, that things like Antarctica is too big. That's not the correct, you know that from Google Maps and other. And here it's OpenStreetMap. It's also possible with volume. I don't have time to show that. It's also possible to add different maps. You can even add Google Maps. You can add Esri maps. You can add whatever map, Bing Maps, and even your own mapping services. So let's look. You can also do styling. I will skip that because of time. And remember our data set from before with the big cities with more than 10 million people. I can take this one and big cities, I can take this one and just add some markers. I just use volume marker, add to the world, and here we have some markers of these cities. I can even create in this function the name. A pop-up is a string. So if I click here, you see I can add some text. In this case, Istanbul with 14 million people. So I can save this map, save my map HTML, and I have a map with this city dataset. Okay, and this last example we will skip because of time. This just shows the route, the geodetic line between Minsk and New York. So you see, this is the shortest distance. You can do all these things with these libraries. So, if you are interested in more geo, there is one way. There is a GeoPison conference I'm organizing every year. It's Geo plus Python, and it will take place June 24, 26 in Muttenz, Basel, Switzerland. And if you say, okay, Geo is great, but not my thing, and you say, oh, Basel is a nice city, then there is the EuroPython also in July 8 to 14 taking place in Basel. So there are even people coming to both. So don't forget that. It's always a great conference. Here are the links again. Thank you very much.
Thank you, Martin. I think there are several people here who are like profs in GeoPython, and I'm pretty sure they liked your speech as much as I did. So let's wait for complicated questions.
Thank you for the speech, and I have two questions. First, about indexing in GeoPython. Can I, for huge amount of data, does GeoPython support it, or you just used something like PostGIS for it? And second question, what you doing with source geometry, like coastline of Canada is very huge and spent a lot of time processing just without simplification. Thank you.
So the first question was about PostGIS. PostGIS also uses the simple feature access standard, so you have WKT strings out of it, so you can do everything there. Actually, I would see PostGIS is just another way to do that. PostGIS is also using Geos, the library, it's the same library. So you can decide, I want to use PostGIS or I do it in the Jupyter Notebook or with Python, but that's up to you. So it's also, I have to admit, PostGIS is a little bit faster than GeoPandas processing. That's because Python is not, we know that, not the fastest language at the moment. There are some people trying to make it faster. It's a binding, actually, it's calling the C functions, so it should reach the same speed. But to answer your question, PostGIS and this, it's basically the same engine behind it. It's just what you want to do. And the second question, now I lost. The second question was about?
Second about source geometry, like coastline.
Oh yeah, coastline, exactly. So if you have a really huge data set and you want to reduce, is that the question? Do you want to reduce the number of lines? Then I think we have to discuss this because the answer would be too long.
Okay, let's go next.
Thank you very much for your presentation. I have a question about GeoPandas. Is it good for generating heat maps, and especially can it handle very big data volumes, like millions of points?
At the moment, GeoPandas has the same problem like pandas. You can't really load huge amounts of data. You need much RAM. If you have a machine with 64 GB or 128 or 200 GB, then you are lucky. But at the moment, that's not possible to make out-of-core things, but it's planned. GeoPandas people actually are waiting for the pandas people who try to implement this at the moment, and it's a matter of time. But at the moment, it's not usable for really very, very large things. The only thing you have to do it using Fiona and do it yourself by going through all data sets.
Okay, we have time for one more question. And here it is.
Thank you for your presentation. You've shown us plenty of different libraries to process geospatial data. As far as I understand, the geospatial data is kind of raw input, and let's suppose I'm building a machine learning model and I want to extract some valuable features from that data. What best practices can you recommend for feature engineering from geospatial data?
I can tell you what we do. We do some remote sensing things with raster data, for example. We use raster data, satellite images, and so on, and try to find some features. And that's one way. So we use rasterio for that to load parts of the image or whatever we want to do. And the second is with vector data. Every vector data set is different, so I can't give you an answer to that because it's too broad. It's like if you asked me the same question for non-geospatial data, I would not be able to give you an answer because it's case by case. So you have to look at the data first and then create your models. But there is no recipe for everything like this. So of course the coordinate is very important. That's something you need to build into your model, and then the same thing like you do for non-geospatial data sets.
So there is no silver bullet.
Beg your pardon?
So there is no silver bullet on it.
No, it's not possible, unfortunately. So
too bad. So thank you, Martin.
Thank you very much.
I would like to remind once again that you can vote for the speech on this board. And now we will have a pause for coffee and other type of rest. And let's meet here at